E equals MC.
Square. We're squaring
it.
Right.
And what's on the other side of the equation?
Energy.
E. So
Right.
the energy goes as the velocity squared.
Look at that. And that's just...
You've known that from birth.
Didn't even know it.
You didn't even know.
I didn't even know I knew that.
That's right.
Look at that.
There you go.
That's awesome.
Welcome to StarTalk, your place in the universe where science and pop culture collide. StarTalk begins right now.
Chuck, I got another one for you.
Okay.
What shape is Earth?
Sounds like a trick question.
No, it's not. No,
saying.
just what's your first...
Well, I'm looking around your office, and I'm going to say round.
Round, because
there's a lot of globes in here.
There's a lot of round stuff.
There's a lot of round stuff.
Round.
Right.
In fact, in my office, nothing is more than arm's reach away.
Right.
Right. So Earth is round. The moon?
I'm going to say the same thing.
I got moon
There's
up
the
here.
moon.
The moon is round. In fact, this is the correct relative size of the Earth and the
to
moon.
the moon.
Yeah.
Nice.
I got you here. Okay. So the moon is round. How about the sun?
The sun, see, now that's a different story because the sun is whatever it wants to be. See, because both the Earth and the moon are rocky, whereas the sun is like, baby, I'm plasma, baby.
Yeah,
I do
it's
whatever.
all
I
plasma.
do what I want. I do what I want.
It's all plasma, yet it's still round.
Still round.
We got rock that's round and plasma
that's round.
Okay.
Nice.
You look around the universe, round is a thing.
Yes, it is. Pretty much. I mean, unless, of course, you are how shall we say, an alternate thinker. Someone who likes to embrace the unusual.
Something
Yeah.
with the word flat in it.
Yeah, you like discs. You believe in discs. You might
flat
that person.
discs.
Flat discs. So, yeah. But, yeah, no, you look around and everything's round.
Okay.
And if it's not round, it's trying to be round.
Yeah. So there's laws of physics related to that. So when I use the word round, I'm referring to basically something that's spherical.
Right.
Okay? Because technically a circle is round.
Yes.
But if you say circle, it's a circle. There are no circles in the universe.
Right.
Okay?
Right.
Everything
They're
has a
spheres.
shape. They're three-dimensional.
They're three dimensionals.
Right.
Even a black hole isn't a circle.
Yeah, that's right. It's spherical.
Right.
All right. So even in the Bible, it refers to Earth as a circle.
Okay.
Okay, the circle of the Earth.
Okay.
And the Christian apologists who are defenders of the faith
Right.
will say that the Bible knew the Earth was a sphere. But anyone at the time saw the word circle and drew circles
Right.
for all maps of the Earth, with Jerusalem in the middle and water surrounding a
Right.
coastline and demons off the edge of the map. So, but the point is, in the universe,
Mm-hmm.
forces conspire to make round things.
Nice.
Okay?
Okay.
All right. So, let's start with soap bubbles.
I mean, when we're talking about the universe, why not?
Why not?
Yeah,
When was the last time you saw a triangular soap bubble? Never. Okay? No.
I'm
just don't.
sad now. I'm very sad
Because you
I've
have-
never seen a triangular soap bubble
Or cube.
or cube, and now I want to see both of those so bad. I don't know what to do.
So, in a soap bubble, you have this film,
Right.
and the film wants to be as small as possible.
Okay.
Okay? Now, if there's any part of the film that's sticking out,
Mm-hmm.
it says to itself, I can make it smaller than that. Okay?
Right.
So all parts of the film want to make the whole structure as small as possible.
Okay.
And there's only one shape that accommodates that, and that's a sphere.
Okay.
Now, here's what's interesting.
Mm-hmm.
For a given amount of material,
Mm-hmm.
surface,
Mm-hmm.
the shape that contains the largest volume is a sphere.
Okay. Got you. Right.
Oh,
I see what
that's
you're
an
saying.
interesting
That is.
fact. Okay?
Okay.
So if you have a nice spherical fruit,
Mm-hmm.
okay?
I'm hungry now.
If you make that any other shape,
Right.
it's going to bust out the side.
Right. I know that because I have stepped on many oranges.
Why doesn't the orange just quit? No.
It's just right out the side.
Right out the side.
Exactly.
Okay?
Right.
Same thing will happen if you step on a water bug. Just pops right out.
Does yes.
They're not spheres,
Right.
but they're trying to be.
Right.
All right. So,
And in my old neighborhood, you could hear them scream.
scream.
That's how big they were.
They say, get the hell off of me.
That's a serious water bud. Man, what the hell? The hell off of me.
Back your ass up. Can't you see I'm walking here?
That's funny. I'm walking over here. That's funny.
All right.
Okay.
So this thing with spheres, what it also does is brings the material inside of it as close to itself as it can possibly be.
Nice.
Once you start flattening it out, the parts that are farther away from other parts than they would otherwise be if it was in a sphere.
Okay.
Okay. By the way,
Right.
have you ever seen a cold pigeon?
I don't think I've ever seen a warm pigeon. So I'm not.
You don't know the difference.
I don't know what the difference is.
Okay, if you look at pigeons, we're in the city here, so I'm referencing pigeons.
Of course, yes.
Look at birds in general.
Right.
They're warm-blooded.
Yes.
How do they stay warm? First, they have like feathers,
Right.
which are highly insulating,
Right.
which is why we yank them off birds and stick them in our coats.
Right.
Okay.
Yes, exactly.
And all right,
Called down. It's called down.
down. Right. All right. So the bird gets as round as it possibly can.
Oh.
Just take a look at
that's
a pigeon in the
right.
cold.
Yeah.
It is round.
They puff up.
They puff up and they're round.
as they can, yes.
And that way, there are no extremities at risk. They've reduced how flat or extended they would otherwise be. Okay? So even cold pigeons want to be round
Nice.
for thermodynamic reasons.
Cold
Okay.
pigeon sounds like the worst hood liquor. that
Cold
you
pigeon?
It's like, what you
Worse
drinking?
than cold duck?
Yeah, worse than cold duck.
Cold pigeon.
Oh, man, I can't afford cold duck. You must be rich. I'm drinking cold pigeon.
Pigeons, I tell you, pigeons get no respect.
Oh, man.
You know what their formal name is
No.
in the wild?
No.
Rock doves.
Rock doves.
Yes. And they evolved in canyons.
Okay.
And they swoop down and up in the canyons, and they live on the walls of the canyons.
Rock doves.
Right. And so cities, what are they if not steel
Yeah,
canyons?
that's absolutely
There
right.
it is. And we share our space with them.
Yes, we do. And our shoulders with with their leavings. And supposedly that's good luck.
All right, so now let's get out of the Earth and go into the universe. If you gather matter together in the universe, you can say, well, what shape will it take? Well, if it's rock, the rock is happy being a rock.
Okay.
It'll be whatever shape the rock is.
Mm-hmm.
Most asteroids just look like rocks.
True.
All right. Some of them may be Idaho potatoes, but they're not spherical
Right.
because they don't have enough gravity to overcome the rock.
Right.
The structural integrity of the rock is what's determining the shape of the asteroid. Above a certain size, the gravity of all the material overcomes whatever the rock wants to do by itself.
Mm.
And the high places, the material will fall into the low places,
Mm-hmm.
and this will continue until basically you have a sphere on your hands.
Look at that.
So, one of the criteria for the definition of a planet
Uh-huh.
is it big enough to be a sphere?
Right.
Pluto satisfies that criterion.
Uh-oh, watch out.
But
Might have to make a retraction
no, there are other rules. Pluto fails, but it satisfies that one.
of being round.
Being round.
Uh-huh.
It has enough mass for it to structurally, because this is gravity at work. Gravity says, everybody come to the center.
Mm-hmm.
And there's only one shape that can get the most number of people as close to the center as they can possibly be, and that's
a sphere.
a sphere.
Right.
Exactly. Pluto's moon is even a sphere.
Wow.
Charon.
Sharon!
Now, why is the moon called Charon?
I don't know.
Charon is the ferry boat driver who takes your sorry ass across the
hell?
river Styx to Hades.
Hades.
Yeah, to
Right.
where Pluto is.
Right.
Well, it's the Greek
Right.
version of the Roman.
Yeah.
So that's how we name our moons, the Greek counterpart in the
Nice.
life of the Roman god, if the Roman god were Greek.
Right.
Right. All right. So let's keep going. The sun,
Mm-hmm.
it's got badass gravity
Yes.
and it's got gas.
yes.
It's holding on to its gas. Where's
I'm sorry. I couldn't help it. I'm so juvenile.
I know. That is like, are you 8 years old, Chuck? You can't resist the scatological.
I didn't make a joke, but I couldn't
You just
stop
laughed at
laughing.
it. The sun generally holds its gases.
Yes.
Occasionally there are effluences, which we call solar flares.
Yes.
Okay?
Exactly.
All right. So, the gas, it's trying to get to the center of the sun too.
Right.
Everybody's trying to get to the center of the gravity. The shape that results from that is a sphere.
Okay.
Period.
That's it.
That's all it is. All right. And this persists for every star, for every planet, for large non-planets,
Right.
like Pluto. One of the asteroids Pluto got demoted with this new rule, but there's an asteroid that got promoted.
Okay.
The asteroid Ceres,
Ceres.
the largest asteroid,
asteroid.
okay, named for the goddess of harvest,
Okay.
and that's where we have the root for the word cereal.
Oh, nice.
Ceres, cereal, okay?
Right.
So-
Cereal.
Ceres was the only spherical asteroid.
Right.
So it satisfied the sphere criterion, but it didn't satisfy the other two. So it graduated to dwarf planet.
oh, look at that.
Yeah. So Pluto had company in this new. Pluto got demoted, others got promoted, and now they got a new family.
They
there.
got a new family.
All right.
Dwarf planets.
Okay. So we have the laws of surface tension. I didn't use that term at the moment. The laws of surface tension help us create soap bubbles.
Right.
It's also what beads up liquid if you just waxed your car.
right.
It wants to be a sphere
Right.
so bad. And every part that's not touching the car is round. All right?
Exactly.
All right? If you dripped liquid in 0G,
Right.
surface tension, pop that into a sphere
Right away.
straight away.
Yeah.
There's a scene in Star Trek.
I know what you're talking about, where they shoot
They shoot the Klingons in
right,
the room.
and there's
There's one of the
zero
movies.
G because they turned off the artificial gravity in the ship, and the blood
The blood spews out
all in big droplet forms that are round,
spherical blobs.
Yeah.
And people after that said, that's weird. They must have weird blood. No, your blood would do that too
Right.
in 0G.
Right.
But in 1G, the blood goes down and drops on the ground.
right.
Okay? Now, in 0G, you can make an arbitrarily large blob of liquid unless you bring it into any kind of G at all. And then the gravity overcomes the surface tension and it flattens out.
Right.
That's why you can't just haul a blob of water out of the ocean and, put it in a display case as a sphere.
Right.
Earth's gravity overcomes that.
Right.
Okay? So it's a contest of forces at all times. Earth's gravity overcomes the rocks. The sun's gravity overcomes the gas. Everybody gets a sphere out of this. So in the universe, you have exceptions to this when you have rapidly rotating objects.
Okay. All right.
Guess what happens to them?
They flatten out.
They flatten out.
Mm-hmm.
Saturn rotates once every something like 10 hours.
Wow.
Saturn is big and it rotates twice as fast as we do.
That's
My
serious.
boy's flattened.
Yes.
10% flattened. It's 10% shorter pole to pole than side to side.
Wow.
Next time you look at a photo, check that out. You can notice
You
it
can
easily
notice it, right.
with your eyes.
Okay.
So
How about the rings? Are the rings rotating at the same as rate as the planet?
No. They're rotating.
Or they're rotating in the planet independently?
according to their own orbital
Each
physics.
one of them has their own orbital physics.
So why aren't they a sphere? Well, when the moon formed, because we got slammed by a protoplanet in the early universe, in
Right.
the early solar system,
Right.
we had a ring of debris.
Mm-hmm.
But some debris was a little larger than other debris, which means it had a little bit more gravity than the other. If you have a
Right.
little bit more, then you get a little extra stuff. Now you have even more gravity.
Come join me. One of us. One of us.
And so this is a runaway process.
Right.
So the ring coalesces to become
The moon itself.
our moon itself.
Wow, that's great.
Yeah. And so you get the sphere ultimately.
Right.
And one of the saddest moments in my professional life was reading a research paper on the dynamics, the orbital dynamics of the particles in Saturn's rings. And they said it's a temporary phenomenon.
Oh,
That was sad.
that is. That means Saturn's going to lose its ring.
Yes, and that it probably
Oh.
didn't have its rings 10 million years ago, which meant the dinosaurs, if they had telescopes
They would have
and
ne-
looked at the Saturn, it would have had no rings.
Look at that.
That's sad.
That is sad.
That's sad.
Mm.
So anyhow, I wrote a whole essay 25 years ago called On Being Round.
On being round.
I think it's online too. Just
Nice.
go On Being Round and Tyson. So search deGrasse, just in case Mike Tyson did something round.
That's right. I have a thing called stick around. Stick around. That's why I tell you.
You better be glad he ain't here to whoop your ass. Imitating him.
I wouldn't stick around for that. That's the whole point of my thesis.
So you search for On Being Around and type, you get the full discussion there.
Nice.
Or you just heard this, so you don't even need to read it.
Exactly.
It's a 2,000-word essay.
Right.
If you want to check it out.
And for all of you disc lovers, you flat disc lovers, there you go. This is why, what you believe is stupid.
Oh, the flat Earth folk. Yeah. So, and our galaxy is very flat.
Right.
Okay. When it formed.
Right.
Okay. As it formed, material falling from the top and the bottom was gaseous. It stuck together in the midplane and then formed stars there.
Right.
Because the gas clouds they don't pass through. They stick together like hot marshmallows.
Right.
Touching, in midair.
Yeah.
So whenever you find something that's not a sphere, there's a fascinating reason why that's the case. But the natural state of the universe is, and black holes, there's non-rotating black holes is sphere. If you want to rotate it, it will flatten out,
right,
as rotating things do, and you'll get like a torus or a donut.
No.
So rapidly rotating black holes are actually donuts, which are still kind of round.
Yeah, exactly.
In their own way.
Yeah.
Yeah.
I'm Nicholas Costella, and I'm a proud supporter of StarTalk on Patreon. This is StarTalk with Neil deGrasse Tyson.
Okay. Lines in the sky.
Lines in the sky.
Okay.
All right.
All right. So, let's start.
All right.
Okay? You're standing there.
Okay.
And you're looking due south.
All right.
Okay?
Okay.
You take your hand and draw a line from due south,
okay,
directly overhead to due north.
All right.
You do that. Okay?
Okay.
That line has a name.
All right.
Yes, it does. And by the way, it's not the same for everybody.
Mm-hmm.
If you go east of me,
right,
you're going to make your own line.
Right.
North to south.
Right.
Okay? So everybody, depending on where you are in longitude on Earth, you're going to have your own line.
Okay.
Okay?
That makes sense.
Okay. That line has a name.
Okay.
You know what it's called?
No.
The meridian.
Okay.
The meridian.
We'll call it Murray.
Now, I need you to remember this.
The meridian.
The meridian.
Okay. It's a great hotel, by the way.
Okay. All right?
Yes.
So the meridian. Everyone has a meridian, and it goes directly over their head, connecting due south to due north.
Okay.
That's one of the lines in the sky. Okay.
Okay.
The sun, when it rises, okay,
mm-hmm,
works its way towards your meridian.
Okay. Yes. Watching it. It's coming.
Coming from the east.
It's there.
No. It's coming from the east.
Right.
And it'll cross your meridian.
Right.
Go to the other side of your meridian and then set.
Okay.
Okay?
That makes sense.
Okay. Do you know what AM stands for?
AM, after midnight.
No.
Okay. Oh, let me think. Something meridian.
Antemeridian.
There you go. So ante.
Like antebellum.
Antebellum. Before.
Like antemeridian.
Antemeridium.
Before the meridian.
Right. And so then PM must be post
meridian. There you go. It's where we get AM and PM from.
I thought AM was after midnight. But then when I thought, then what would PM be? Pre-midnight? Well, this makes no sense. Antemeridian.
And post-meridian. Okay.
Cool.
Two whole concepts that rely on your meridian.
Right.
We'll start there. Okay. Let's keep going. You ready?
Okay, let's keep going.
Okay. Earth's equator,
mm-hmm,
if you extended it out to the sky,
okay,
there's a line on the sky that corresponds to Earth's equator.
Okay.
That's called the celestial equator.
All right.
Okay.
That's cool.
We together?
I'm with you.
You with me?
Yeah.
We good?
I'm good.
Okay. All right. Now, there is a line that crosses There's another line, circle on the sky. The Earth's equator is a full circle on the sky.
Right.
Because the equator is it goes around the Earth.
It goes around the Earth.
Everybody on the equator looks up. There, it's right there.
Okay.
Overhead. For everybody else, it's at an angle.
Mm-hmm.
Okay. So, there's another line that crosses the celestial equator. So think of it as two rings at an angle to each other.
Right.
Okay? This ring crosses the celestial equator at an angle of 23.5 degrees.
Okay. All right. That makes sense.
Okay?
Okay.
23.5 degrees.
23.5 degrees.
That line
Mm-hmm.
is the path throughout the year that the sun takes against the background stars. Of course, the sun is not taking a path.
Right.
We're going around
it.
It.
Right.
But let's be pre-Copernican here, just to make the discussion simple.
Okay.
So day by day, the sun moves a little bit along that
line.
That line.
Right.
Okay?
That makes sense.
Okay.
Yeah.
Got that?
Yeah.
Okay. The moon has its own line.
Okay, but this is way too many lines. We're getting a little crazy with the lines.
Okay.
Okay. So now first we got the celestial equator.
Yes, the celestial equator.
Now we got the meridian, which
The
is your
meridian.
own personal line. And then we have the line that is at 23 degrees.
Angled. Okay.
Right.
And that's the path the sun takes.
That's the path the sun takes.
Okay.
All right.
Okay.
I'm still good.
Now, why is it 23.5 degrees?
Because we're tilted that way.
That is the tilt of Earth.
Okay.
Okay?
All right.
Earth is tilted that.
Yes.
And because we're tilted,
right,
the sun doesn't line up with our equator. If we were not tilted, that path of the sun would be right on Earth's equator.
Nice.
It would have been interesting and different.
Exactly,
okay?
Right.
But now we're tilted, it means we have seasons. Because the tilt gives us seasons. All right. So now watch. The moon, in its path around the Earth, has its own
line.
Its own line.
Right.
Okay? Okay? That's angled 5 degrees to our equator. Okay?
So, right.
Okay.
Okay.
So,
okay. All right. I got you.
if the moon is crossing the path of the sun, at the same time the sun is in that spot, you get what?
An eclipse.
An eclipse.
Right.
So this path the sun takes around the earth is called the ecliptic, because that's where you would get an eclipse.
Nice. Okay.
Ecliptic.
The ecliptic.
Yes.
All right.
Yes. That's the sun's path around the earth. Okay? Anytime the moon intersects it, if they're together, eclipse.
Bang. All right.
We call it the ecliptic.
Okay.
All right. Now, if you want a way to think about it, a loose way to think about it, how far does the sun go every day along that ecliptic? All right, how many days are in a year?
365.
How many degrees in a circle?
360.
Ah!
Look at that.
The sun goes approximately a degree a day.
Right.
Is that cool?
That is very cool.
That's very cool. A degree a day. So in a month, it goes a month. So a month is 30 degrees.
30 degrees.
So a degree a day goes 30 degrees across the sky.
Okay.
Just add all that up. Okay? So more lines. I ain't done with you.
Wow. There's more. Damn, it's got more lines than the damn subway.
Okay, you ready?
Go ahead.
Earth's longitude and latitude,
All right.
you can project that onto the sky and have a grid system on the sky.
Right.
We have that. And our longitudes become what we call right ascension. And the latitudes become what we call declination.
Okay.
Okay? And right ascension is measured in hours, and the declination is measured in degrees. So every object in the sky has a coordinate in right ascension and declination.
Which corresponds from the grid that we project onto the
For
sky.
the
from our
style of that
longitude.
grid, we project onto the sky.
I got you.
Okay? But that's the closest that, other
Right.
than that, there's not. Okay.
There's
nothing.
I got you. Right.
All right?
I understand.
You're not going to say, well, here I am on Earth. Where's my spot on the sky? That's not going to happen.
No,
Okay?
right, no.
But just if you want to think about the orange wedges of longitude on Earth and the horizontal slices across, we've done that with the sky.
And then whatever's up there, that's what that is.
Correct.
Right.
Okay.
Okay.
So if you look at a star map, you'll see this grid.
Right.
That's how we know where anything is. That's how we tell a telescope to find something on the sky.
I was going to say that's when you look up and you find any celestial body in a telescope.
In a telescope,
they say,
it's got coordinates.
That say the ascension, right ascension,
and declination.
And that gives you the plot point.
It's degrees, minutes, seconds, and it's hours, minutes, seconds, just kind of the way we have here on Earth.
Cool.
Okay? Okay.
Cool.
All right. Except we have hours for our right ascension. Here, our longitude is still in degrees, but we could have measured it in hours because it's 24 hours around. We just didn't. Okay. All right. So now, the North and South Pole have spots on the sky.
Okay.
North and South Pole of the Earth, project them out to the sky, you get the North Celestial Pole and the South Celestial Pole.
Okay.
Got that?
Right.
Okay. Our South Celestial Pole is near Polaris.
All right.
The North Star.
Okay.
It's not actually pointing to Polaris. It's like 2 full moons widths away from it.
Okay.
Okay, something like that. It's not point. So it's just kind of near it. And people say, "Oh, we have a pole star. There's something divine about that for our navigation." And no, it's just sort of near it.
Sort of near it. Right.
Okay? All right. Earth, tilted and spinning on its axis, tugged on by the moon, actually wobbles.
Uh-oh.
Okay. It wobbles.
What happens to all these lines?
I'm about to tell you.
Oh, my God.
Watch. Here you go. You ready?
Here we go.
Okay. So, the North Celestial Pole precesses in a circle on the sky
Right.
once every 26,000 years.
Oh, my God.
So the North Pole traces a circle on the sky once every 26,000 years.
Wow.
All right. Which means the North Star, Polaris, only happens to be our North Star now.
Right.
Okay? In the days of the Egyptians, 5,000 years ago, it was not pointing to the North Star.
Right.
I think, I got to check my notes. It was pointing to a Thuban. There's some other star, which was the pole star for the Egyptians.
For those guys, right.
Okay? Different pole star.
Wow.
All right.
Wow.
And I think we'll
take that, Zodiac.
I think we'll get a little closer to the North Star before we go away from it again.
Okay.
All right. It's a 26,000 year cycle. Okay? All right. And it drags our grid with it.
Okay.
Because the grid on the sky emanates, it matches the grid on the Earth. But how about the stars? What coordinate are they if we're dragging the... So, this freaks people out if they hear it for the very first time. Every coordinate we have for objects in the sky have a date. That is the coordinate they had at that date.
Oh, wow.
And so we all agree. Are we referencing the year 2000?
Right.
January 1st at midnight? Okay. Boom. You give the coordinate and you give a date. Then you hand that to your computer, hand that to your telescope, which is talking to a computer, and the computer says, let us precess the coordinates of your object from that date that you gave it to tonight. So it'll precess the coordinates.
Wow.
From the year 2000 to the moment you were observing that object. So the grid system is not constant.
Right.
It's crazy.
That's insane.
Yeah, and before we had computers doing this,
somebody had to do it by hand.
Yes.
Oh my God.
We had to precess the coordinates by hand using something called spherical trigonometry.
Wow.
Yes. Spherical trig. And it used to be an entire graduate course in astrophysics. And I got into graduate school just when the computers started taking this over.
Right.
And I did not have to. And the name of the guy who wrote the book on spherical trig, his name is Smart.
Well, guess what? He's dumb now. All them royalties dried right up. Oh, what a shame.
Yeah, because it was like, I ain't doing this. I don't have to do this.
I don't have to do this.
I don't have to do this. Now, a consequence of this,
right,
of this grid shifting, is that the constellation in the sky that the sun was in at that month of the year has also shifted.
Right.
Up. So 2,000 years ago,
Exactly.
when they're laying out the constellations that the sun moves in front of, and they decided there's 12 of them, and they called them the zodiac because there's animals at zoo. The zoo is the key.
Right.
The key.
So zodiac.
The zodiac, okay? They were all lined up for astrologers 2,000 years ago, okay? So 2,000 years ago, when all these were laid out and the boundaries and the houses and everything, what fraction of 26,000 is 2,000?
2 times 13, so 113.
It's 113,
Right.
which is not that far from 112.
Right.
Okay?
Okay. Oh,
This is my saying.
Oh!
This is what I'm saying.
That's where we're going.
So
I see
all
it.
these constellations are shifted by a whole constellation along the zodiac.
That kind of messes up the whole premise, though, doesn't it? Like,
You telling me? You telling me that?
I'm
You
like,
tell me. I'm just, okay. So
if I'm born in a certain month,
correct. The month was when the sun was
when
in
the
that
sun was in
constellation.
that constellation.
It's a completely other constellation now.
Oh my God.
Correct. So
Wait a minute.
what?
I'm so sorry, guys.
Okay.
This is worse than Pluto for you.
Because it got set up 2,000 years ago.
Right.
That's when it got, not in ancient Egypt, 2,000 years ago, it got set up. Everything's shifted by a constellation. Plus, the sun has another constellation it goes into, Ophiuchus. So the sun, the sun passes through 13 constellations, not 12. So, but
Wow.
they didn't tell you this. So, in fact, the sun spends more time in Ophiuchus than in Scorpius.
Well, that's because, Ophiuchus is hard to say. So, Scorpius is easy.
Okay. So, if you thought you were Scorpius, you were probably Ophiuchian. And all Scorpions and Ophiuchians are currently Librans.
Yes, and they're also really sex crazed. I'm very sex crazed. I'm an Ophiuchian scorpion. Anyway, that's the deal with Scorpios. They're supposed to be into sex.
Oh, is that right?
Yeah,
I
that's
didn't
what
know
they
that.
say.
Okay.
But clearly you're not because you're Ophiuchian. Okay.
So, this ecliptic, which is where you find the zodiac,
Right.
is
That is
shifted
the
against
line
the background
that's-
stars.
That's right.
Okay? It's shifted against where the sun is on the month of the year.
Right.
So these are your lines in the sky. I'll tell you just a couple more lines and then we'll call it quits. Okay? The Milky Way
All right.
is this band of light.
Right.
Okay? I think if the Romans used the word street instead of way
Mm-hmm.
to refer to their thoroughfares, because the Appian Way,
Right.
this is the way, okay? It would be called the Milky Street.
Right. Because it looks like a road.
It's
That's
a
why
road
they.
across
That's
the
why
sky.
they. Right.
The-
It was
the
like a road of
Way.
Milky Way.
Right.
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 Oh man! Thank God they didn't though, because that's a lousy candy bar.
Milky Street.
The Milky Street.
You don't want that
I
candy
don't want to
bar.
eat that. Well, have a little bite of my Milky Street.
So,
Nobody want that.
so the plane of the Milky Way
Right.
has a line associated with it, and we call that the galactic equator.
All right.
That's another line on the sky.
Another line on the sky.
You follow that around, the Milky Way is puffy on either side of that,
Nice.
all the way around the sky.
Cool.
Right. So it turns out the center of the Milky Way goes directly overhead when seen from the southern hemisphere, from like 30 degrees south.
Right.
My PhD thesis focused on the center of the galaxy,
Nice.
the bulge in the center of the Milky Way galaxy. And to see that best, all my data came from Chile, in the mountains of Chile, the
Oh.
Cerro Tololo Inter-American Observatory. I spent like half my time in graduate school on that mountain, obtaining data,
Wow.
communing with the cosmos.
That's super cool.
Oh, yeah.
I'm jealous.
So we got the meridian. We got the ecliptic.
The ecliptic.
We got the moon's equator. It doesn't have a fancy word. It's
Right.
just the moon's
Moon's
the moon,
equator, right.
path of the moon. We've got right
the-
ascension declination lines,
Mhm.
and we've got
The celestial equator.
the celestial equator
Right.
on top of, and we got the north and,
north
south
and south.
celestial, and you have the precessional circle.
Wow.
Okay. So all those are lines on the sky.
Well, you did it again.
What?
I thought this was going to be a bunch of crap.
What?
When you start out with lines in the sky, I'm like, where can we go with this? Ugh, this is terrible, but this is great.
Yeah. So and now you know what AM and PM stand for.
And yes, ante-meridian
Yes.
and post-meridian.
And by the way, when
And
I
my
was
own personal meridian.
Oh, that's what PM stands for.
Yeah, right.
When I was a kid, 4th grade, we went on a walking trip to the neighborhood post office
Right.
to see the machines. You know, it was a field trip,
Yeah,
right?
yeah,
Right.
yeah.
So I noticed on the door, it said what time it opens, okay? And it said it opened at like 8 or 9 a.m., okay? And then it said 12, and then it continued on to the PM and gave another set of hours, and the 12 just had an M next to it. And when I was a kid, I said, why does it just have an M?
Right.
That's meridian.
Meridian.
That's 12 noon,
12
the
noon.
middle of the day.
Wow, that's even a new thing we all just picked up. What time will you want to meet? Why don't we meet at 12 m? Man, what the hell are you talking about? 12 m, my friend.
I think traditionally, the noon is given the PM.
Right.
Because by the time you say noon, it's already
post-meridian.
It's post-meridian.
Right, yeah.
Right.
But still, I'm right at 12.
Right. Not a millisecond
pass.
Or before.
Right. Or before. Yeah.
Yeah. So there you go.
That's great.
Lines in the sky.
Nice.
Okay. Chuck, I got another one for you.
Okay.
All right. So you've seen or read about or heard that when spacecraft come back to Earth,
Right.
they have heat shields.
Yes, of course.
And otherwise they'll burn up.
Yeah.
So the heat dissipates the energy, the kinetic energy of the craft until it can just deploy parachutes and land
Gently
smoothly.
waft down
Yeah,
to
correct.
the Earth's surface.
Unless you're Russian.
Right. In which case, you just crash into the Earth.
They don't land in water.
That's right.
They land on dirt,
Yes.
okay?
Because we are Russian. That is right, comrade.
So people tend to have the attitude's not the right word. They tend to think that this reentry
Mm-hmm.
is some very scary part of the trip. And we wish we didn't have to do this, but it's a necessary evil of coming back to Earth.
Well, I mean, it's easy to see why you would think it's a scary part, because every time they show anything coming into the Earth's atmosphere, it is on fire.
It is on fire. Right. But you're thinking, oh my gosh, it's too bad we have to go through this.
Right.
No, that's the wrong attitude.
Ah,
We are glad we're going through it.
okay.
You know why? It means I don't need fuel to slow down.
Oh, there you go. That's right. Yeah, that's right. Because when you land on the moon, you got to...
Yeah, you need retro rockets so that you land smoothly.
Right.
Because there ain't no air on the moon.
Exactly.
So re-entry of Earth's atmosphere is functionally aerobraking.
Nice.
How to take your energy of motion and deposit it somewhere else.
Using the atmosphere as brakes.
As brakes. Correct.
There you go.
Otherwise, the Apollo astronauts, in their case,
Mhm.
or anybody, but especially the Apollo astronauts, would have had to have carried fuel from their original launch pad to the moon, back to Earth, so that they can slow down.
Right.
Okay? By the way, if there were filling stations in orbit,
Oh, okay.
that would be fun, because then they just have to fill up.
Mm-hmm. Watch the window, sir.
Check the oil. They don't do that anymore.
No.
That's old reference,
that's
man.
It, that is.
So how old are you?
Well, no, because I live in Jersey.
Oh, in Jersey?
So we still have those guys.
You
in
still have
Jersey.
full service?
We still have
By law?
Everything is full service by law.
Wow.
So when you pull up, a dude comes out and he's like, "What'll it be?" And I'm just like, "Yeah, see, it'll be
What'll it
fill
be?"
her up, see, fill her up, see, and get me a pack of Lucky Strikes."
And check the oil while you're at it. Yeah, that's like, I forgot.
Yeah, well, I live in Jersey, so
Jersey's-
no matter where you go,
there is no
full serve. There's no self-serve.
In Jersey. Okay.
And they do your windows and the whole deal.
Man.
Yeah.
Okay. All right. So, now where was it? Why are you distracting me like this?
I'm sorry.
And by the way, I forgot what movie it was. Was it Mission to Mars? One of the Mars movies where someone is on a space platform and they fall off and they just fall towards the planet
Right.
and you see them burn up. It's like,
Oh, that is dope.
no, like,
It doesn't happen though?
no.
Like that? Damn it.
No.
Why not? I want them to burn up.
What?
I mean, wait a minute.
It's not how it works. Let me explain.
Oh,
If you're in orbit around the Earth.
Oh, then you're just going to fall around the Earth.
Oh, no, hold it. You're in orbit around the Earth.
Right.
And I...
Push me off a platform.
Hang on. If you're in orbit around the Earth,
right,
and I say, okay, I'm done orbiting the Earth, I just want to be on Earth.
Right.
You have to get rid of your 18,000 miles an hour.
Gotcha.
And the aerobraking will do that.
Right.
Okay? However, if you're on a platform,
right,
hovering above Earth,
right,
okay, as these were, hovering above their destination, and you just sort of fall off.
Oh, well, now you're just falling at...
You're just falling.
You're just falling.
You just, as this configuration was demonstrated, okay?
So what is that? You're just going...
You're not eating up your speed.
You would never...
It's just a vertical speed.
It's a vertical speed.
That you're falling down.
9.810 meters per second squared or whatever it is.
Ooh,
is that right?
Ooh, Chucky, baby. Remembering his metric.
Exactly.
Acceleration of gravity at Earth's surface.
Yes.
9.8 meters per second.
That's right.
Right. So just an acceleration is the rate and change of your speed.
Right.
That's why you have to be per second.
Right.
Right. So after 1 second, you're going 9.8 meters per second.
Right.
After 2 seconds, you're going...
Well, 9.8 twice.
Times two.
Times two,
yeah.
Right.
That would be 19.6 meters per second.
Yeah, I didn't say I was that good.
All right. So the point. So here's what you could do. If you had filling stations in space,
right,
load up the fuel,
right,
and you didn't want to aerobrake because you're afraid of the heat, you load up the fuel, aim your rockets backwards, fire them until you have zero orbital velocity.
Gotcha.
At that point, you just fall. You just fall back to Earth.
Right, and now you can just use a parachute.
Now you just use a parachute.
Yeah, because you're just falling.
You're just falling.
Not a big deal.
Not a big deal.
Right.
There you go.
That's kind of cool. I want that dude to burn up so bad. I don't know what to do, man.
No, just to be clear, if you're falling from very, very far away, like from the moon,
right,
you'll have enough speed. You got to work.
Right.
You're going to need some heat shields.
Right.
Because then your speed is very, very high. Come here. But just stopping your orbit and falling straight down.
Right. All right, so this is off topic. But what are heat shields made of?
Oh, good.
Seriously.
I got you guys. So in the old days,
right,
Apollo era, where stuff was functional and blunt.
Right.
Okay.
That's right.
All right. This shit worked.
That's right. NASA, the way we like it. Like the men who made it. Functional and blunt. That's right. We smoke cigarettes while we calculate re-entry equations. That's right.
With a slide rule.
That's right. We're NASA. Of course we use slide rules to calculate what we're doing. We're NASA.
They weren't all smoking.
Yes,
Come on
they
now.
were.
No, they were not. All right. So the early heat shields of the Apollo capsules, right, and others, but were ablative. So they were layers like an onion.
Nice.
Of material that would burn.
Okay, so you're burning off layers.
Good, right, exactly.
That's brilliant.
And the layers are very insulative. So the outer layer, when it burns,
right,
that it burns completely, and then the next
layer burns.
Kicks in.
Right.
Okay? You don't want to burn the whole thing all at once. That's not going to work. Okay? So it was an ablative heat shield. And what it meant was, if you just come out of orbit, you're going 5 miles per second, 18,000 miles an hour to go to zero. But if you're coming from the moon, you're re-entering at 7 miles per second.
Wow.
Okay? That has twice the energy as 5 miles per second does.
Right.
You know how you know that?
No.
Take 5 and square it. What do you get?
25.
Take 7 and square it. What do you get?
49.
Thank you. Okay? So 49 is twice 25, basically.
Okay. Basically.
So energy goes as the velocity squared.
Nice.
So
go ahead.
So the energy, which is what has to be dissipated by these panels, by these layers, goes as the velocity squared.
Gotcha.
So orbital speed is 5 miles per second. Re-entry from the moon.
That's 7 miles.
It's a 7 miles per second.
Wow.
Okay? All right. You know why 7 miles per second?
No.
Because you had to get to that speed to reach the moon in the first place.
Oh, okay. But wait a minute.
That's called the Earth's escape velocity.
Right.
So if you fall towards Earth from very, very far away, by the time you hit Earth, you are going to escape velocity. Because that's the velocity you needed to have gotten to where you were in the first place. So it's symmetric that way. It's very beautiful.
That is very
in the
cool.
equations.
Now, wait a minute. Okay, well, I was going to ask, is is there a limit to that velocity is there a terminal velocity?
Yes, 7 miles per second.
That's it.
If you fall from the edge of the universe to Earth,
Right.
you'll hit Earth at 7 miles
7 miles per second. So that's it.
That's it.
Woo!
If it's Earth gravity that's
Right,
pulling
that's the gravity.
Because far away is very weak.
Right,
You're
exactly.
not sailing right
no
out.
big deal.
Yeah. So no matter where you fall,
Right.
so in other words, yes, if you fall from the edge of the universe, you're going to hit exactly Earth's escape velocity. If you fall from the moon, as far as the equations go, that is tantamount to the edge of the universe.
Right. Might as well
Most
be.
of the energy that you're going to acquire from falling to Earth happens in the last bits,
Right.
not in most of the early stages.
Okay,
so,
gotcha.
so that's why it's loose, but it's accurate enough for the example.
All right. Now I'm just thinking. So let's change.
So the astronauts probably went 6.8
Okay.
meters per.
So if they were falling,
miles,
go ahead.
so the astronauts probably went 6.8 miles per second
Okay.
to get to the moon.
Oh,
but it's
that's
close
nothing.
enough to 7. Right. It's close enough to 7. So the point is, this velocity squared,
Right.
what's the first equation you ever learned in school?
Actually, the first. Oh, okay. That's not an equation. I don't know. That's
Equals mc squared.
That's
Of
true.
course you did.
That's true.
What is the c in that equation?
It's a constant of the speed of light.
It's the speed. And what are we doing with the speed? E equals mc
Square. We're squaring.
We're squaring it.
Right.
And what's on the other side of the equation?
Energy.
E. So
Right.
the energy goes as the velocity squared.
Look at that. And that's just
You've known that from
and
birth.
Didn't even know it.
You didn't even know.
I didn't even know I knew that.
That's right.
Look at that.
There you go.
That's awesome.
Okay. So basically all of the energy equations.
By the way, you made a very big assumption about me learning that as my first equation. I went to Philadelphia public schools.
Okay. Okay, so you learned it when you were 21. Okay, fine. It's still your first equation.
Exactly. Okay, go ahead.
So that's why the energy is higher. You have to dissipate twice as much energy. So the shields on the Apollo capsules that came back from the moon
Right.
were at least twice as thick.
Gotcha.
And you just ablate.
You're peeling them
You're
off.
peeling them off.
Just peeling them
It was
off.
very easy from an engineering point
Right.
to increase the
Yeah.
heat resistance of the capsule.
Yeah, you're just putting on more layers.
Just putting on more layers.
Yeah, you don't
Exactly.
even have to change the material or anything. Just put
Exactly.
on more layers.
Okay. So the other method that NASA used was invoked for the shuttle tiles.
Yeah, we saw that.
We saw the shuttle.
We
Right.
went to Los Angeles. We saw the California Science Center.
Yeah, the Endeavor.
The Endeavor that's
is on
what it
display
was, the
there.
Endeavor.
It's in captivity
Right.
in the California Science Center. So those it's not ablative because they want to reuse
Right.
materials.
Right.
So this material, you could take a blowtorch to it.
Right.
It's red hot.
Right.
Put the torch down, return to it, and it's room temperature.
That's really cool.
Yeah. So it dissipates heat rapidly.
Right.
As it gets hot, it's radiating it away while it gets hot, like in real time. So
that's
it's a
cool.
beautiful thing.
That's very cool.
So now you're in orbit, you want to get out of orbit,
Okay.
okay? You need some kind of thing to slow you down a little bit
Right.
so that the atmosphere can kick in.
Okay.
So you slow me down a little bit, I drop to a lower orbit
Right.
where there's a few more air molecules.
Right.
Now the air molecules are
Now
hitting
they're
you,
hitting me.
okay?
Right.
I don't have to use my engines anymore because you're hitting air.
That's slowing me down.
Slow you down a little more where the air is even denser.
Right.
Slows you down even
a
more.
little more.
Even denser. Slows
Right.
you down more. This is a runaway process.
Gotcha. Deorbiting.
Deorbiting is as textbook as it comes.
Unless you're Chinese. In which case they say, have whatever happens.
Oh, some of their boosters were not. Wait.
I love how you're trying to defend them because they're your people.
No,
They're
my
fellow
space people.
astrophysicists.
My space
They're
people.
space
Let's
people.
be clear.
Okay, let's be clear.
Anything that deorbits
Right.
will come down rapidly
Yes.
because of this phenomenon.
Of course.
You lose a little bit of, okay, and there's more air molecules,
Right.
and you go to a place where there's even more air molecules.
Right.
So the arc out of orbit is actually pretty steep,
Right.
okay? You want to do this
Mm-hmm.
where it's not going to hurt anybody.
Right.
Earth happens to have nearly a third of all of its longitude spanned by the Pacific Ocean.
Nice.
There's Hawaii in there and the Galapagos
Oh,
and
know.
a couple of islands.
Right.
But
Nothing we really need.
no, stop.
Yeah, no.
But the total area of non-populated ocean
Right.
is huge.
That's great.
So you start your deorbit at a place where you then plunk the thing down in the Pacific.
In NASA's toilet.
The Pacific is the great toilet bowl of space. Yes. So what happened with the Chinese boosters was they did not have a means to control their deorbit.
Right.
And they were just sort of ambling wherever they happen to pick up enough molecules to drop them. That's where it is.
Right.
And
we got lucky.
Yeah. So they could not control. So you want to have a little bit of fuel.
Just a little.
To tell it when to start that deorbit and then drop it in the Pacific. And if you don't, it's actually irresponsible.
Yes.
Okay. And that happened with several Chinese boosters and rocket parts.
Right.
Okay. Right. So that's all deorbiting is.
That's really cool.
It's why you need fuel to land on the moon, but you don't need fuel to land back on Earth.
Nice. Because Earth's atmosphere is your braking system.
Aerobraking. Treat it as this is a beautiful thing. Rather than, oh my gosh, will they survive? I don't know. Well, it's dangerous.
We didn't burn up in the atmosphere. We just had an unfortunate braking mishap.
No. So engineers say about rocket accidents?
What?
They're not mistakes. They're launches that are rich in data.
Oh my. Wow, that is rough.
In data learning opportunities.
That is rough, man.
But you need enough sensors around so that you can actually get the data.
Right.
And not just a visual spectacle.
There you go.
You want to have cameras and
whatever.
Thermometers. Yeah, whatever.
Recordings
of everything. Yeah. Take it back to the lab. Say, okay, here's what went wrong.
Right.
There it is. Oh, one last thing.
Go ahead.
One last thing.
Yes.
The space probe Cassini.
Yes.
Which was sent to Saturn. Spent 13 years orbiting Saturn, visiting moons,
taking pictures,
hanging out,
all kinds of
taking pictures, and then we were done with it.
Yeah.
So you know what we did?
Yeah.
We deorbited it.
Nice.
Okay. Into Saturn.
Okay.
Okay. But it didn't have heat shields.
Okay. Oh. So it burned up.
Vaporized.
Look at that.
Because we didn't want it accidentally slamming. Once we're done with it, we're not monitoring it. We didn't want it accidentally slamming into one of Saturn's moons that later on we want to see if there's life there.
Right.
Because for all we know, somebody sneezed on the spacecraft.
Right.
And it goes to...
and we killed all the life on the Saturn moon.
With our sneeze virus.
Our sneeze virus.
So that's a case where it was deorbited, but with no hope of survival.
Gotcha.
Now, when it's time to take the space station out of orbit, that's a big mama jama.
That's huge.
Do you realize the space station has the area? It's the extent of a football field.
I did not know that.
When you include the solar panels and all the modules,
all of it together,
all of it together.
Wow, a football field in space.
Yeah, there'll be a day when we're done.
Right.
We are in the international
now. Do they bring
partner,
that whole thing down at once, or do they?
It's not designed to be brought back in one piece.
Oh snap!
In one shape. Okay, so if you're going to deorbit any of it or all of it, you're going to plunk it into the Pacific as we did everything else. And keep it. It's been up there for 25 years, something like that.
Look at that.
Yeah, I know. So we're proud of it. But there comes a time when we have better technology, better computing, better materials, better everything.
Right.
And we'll do it. All right. That's all we got time for. All right. Neil deGrasse Tyson here for StarTalk. And by the way, we are recording in my office.
A cosmic crib.
I don't think the authorities would sanction that.
Gotta go for it.
In my office at the Hayden Planetarium of the American Museum of Natural History. This space, otherwise known as
the Cosmic Crib.
All right, Neil deGrasse Tyson. Keep looking up.